Hello, today we will introduce the paper Distilling a Neural Network into a Soft Decision Tree. It was written by Nicholas Firth and Jeffrey Hinton. As can be inferred from the title of the paper, it is a paper that combines neural network with decision tree. Firstly, I will introduce the neural net. The neural net show the excellent generalization abilities depending on their use of distributed representations in their hidden layers. But these representations are hard to understand. The story the author want to talk about in this paper is that although neural net's performance is good, but it is difficult to explain classification decision a little. So it would be nice to take knowledge and express hierarchical decisions through neural net. As you can see in the slide, there are multi-hidden layers in deep neural net. For the first hidden layer, we can understand what causes an activation of a unit, and for the last hidden layer, we can understand the effect of activating a unit. But for the other hidden layers, it is much harder to understand the cause and effects of a feature activation in terms of variables that are meaningful such as the input and output variables. By contrast, it is easy to explain how a decision tree makes a particular classification because this depends on a relatively short sequence of decisions and each decision is based directly on the input data. I will give you an example. This is a simple example how the decision tree make decisions. When input was one of the kind student, the given decision tree determines whether this person learned AI or not. At the first note, it asks that, are you interested in AI? If so, the decision tree takes the right path, otherwise the left path. In this case, the lure is whether or not the input is interested in AI learning. Then we face new lure. Have you ever taken an AI courses? In this case, the path is selected in the same way as in the previous case. From this example, we can easily understand why decision tree is explainable. If someone asks why the input came out like this, we can explain the decision tree decision process with conditions at each node. To sum up, neural net is powerful performance but hard to understand cause and effect. Meanwhile, decision tree is easy to explain, but its performance is not good comparing to the other model. Thus, this paper suggested a model that can compromise the interpretability of the decision tree and the powerful performance of the neural net to some extent. The author said that they propose a novel way of resolving the tension between generalization and interpretation. How? They just mimic the input-output function discovered by the neural net. In this step, we can understand neural net is teacher and decision tree is student in teacher-student learning. By imitating the output of the teacher network, at this time neural net, learned in advance student here decision tree, improves the performance even if it has relatively few parameters. Generally, this methodology is called knowledge distillation. From now on, the question of how to transfer neural net knowledge to decision tree comes to mind. This issue is investigated in this study, and we will introduce this in remaining part. So, how did the author mimic neural net? Because the original decision tree made decision with hard lures, the author proposed a new rule to increase the performance of the decision tree. What was applied at this time brought the rules of the neural net, and it can be thought that knowledge distillation occurred in this process. The word mimic is used to use the input-output function of neural net, which means the expression Wx plus b, used to move from layer to layer of neural net. The self-decision tree, FDT, consists of Pi's inner node and Q's leaf node, and the formula for each is as follows. First, let's see Pi. At each inner node, I has the probability of taking the rightmost branch, where x is the input to the model and sigma is the sigmoid function. With learned filter Wi and bias Bi, input x will be matched Pi by sigmoid function. Second, Qk. It means the probability distribution at the else leaf with k output classes. By applying softmax function, final outputs are normalized to represent probability distribution for the k classes. To better understand, I would like to introduce an example. If you look at the equation in the first, second, and third inner node, you can see that each has a different weight and bias, but the input is the same as the X vector. When we think of a general neural net, when we go to input hidden 1 and hidden 1 to hidden 2, we calculate with only the values from the previous layer. But in SDT, each inner node is made through a different weight than X vector. Unlike the original decision tree in Intro 2, in this case, as W and B is learnable, it can be updated, the performance of the new model may be improved. In addition, self-decision occurs well by spitting out probability values rather than true or false values of 1 and 0. What which inner node does only express the probability of going to the left or right of the next inner node. Also, the author put hyperparameter beta inverse temperature. In order to avoid very soft decision in the tree, they introduced an inverse temperature beta to the filter activation prior to calculating the sigmoid. The graph and chart below shows the change in sigmoid shape and value according to the beta value. If it powerful when Pi is near to 0.5. With this value, it is difficult to select a specific node. At this time, it is possible to prevent the decision tree from becoming very soft by multiplying by an appropriate inverse temperature beta.
For the remaining part, we are going to introduce a way to train our self-decision tree model. Essential part of this training starts from the loss function. Loss function wants the model to follow a certain target distribution. This desired target distribution can be in two kinds. One would be a hard label, which is represented as a one-hot vector, and the other would be in short form, which is an input from the neural net. With soft labels along with hard labels, it is possible to successfully transfer the knowledge of neural net to our decision tree. So for this purpose, authors suggest a loss function in the form of cross entropy. What described here is the loss function for a single input x. The term consists of mainly three parts, T, Q, and P. T is the target distribution, and Q is the model's output distribution at each leaf node. Inner parts of this term calculates cross entropy of these two distributions. And for each leaf node, this cross entropy term is weighted using the probability of reaching that node. Although the loss term is simple enough, I want to share a single discussion point here. One might be wonder why the log is taken for this weighted sum of cross entropy term. Our model is a decision tree model, and this model has an exponential increase in the number of leaf nodes. As our loss calculates cross entropy for all of the leaf nodes, our loss term may diverge as we have exponentially many terms. Although the authors did not explain the detailed reason for this, we suspect that there might be one practical reason for this. If the loss term without the log is summed up, we might end up having exponential increase in this term. What do you think? If you have any other opinion, please share your idea with the comments below. To summarize, a loss term calculates the difference of target and model outcome distributions for all leaf nodes. Next, the authors include regularizers. The purpose of this term is to force the amount of inputs that goes left or right to be similar. Otherwise, what will happen? If the probability of going left at node I is going higher and higher, we are using the only left subtree and the right subtree is not being utilized. In other words, we are not using all of the resources that we have. How did the authors resolve this problem? In order to achieve this, we can define the probability of taking right node at alpha I. Alpha I consists of two components. One is large piece of I, which is the probability of reaching node I from the decision tree, and small piece of I is the probability of taking right path at node I. Therefore, alpha is defined as a probability of taking right path calculated from inputs called x. Next, our random variable have two choices, taking left and taking right. We want this probability distribution alpha and alpha 1 minus alpha to be close to half and half. Term C applies cross entropy for this, for the purpose of making two distributions similar. Finally, lambda specifies penalty strength, and the author says if this term is set proportional to 2 to the power of minus d, where d represents the depth of an inner node, it makes better results. And here's the second discussion point. What would be the rationale behind this? Reason for this maybe is, as long as we understood, contrary to the inner nodes close to the root node, inner nodes close to the leaf nodes may want less penalties as they need to distinct dataset based on specific characteristics. Although the same rationale that had been applied to the loss function may exist. As we go deeper, there would be exponentially many terms, so some of those may diverge easily. It may stabilize the training of the network. If you have any opinion for this, please don't hesitate to leave comments. Final thing to do is to take a look at how this model does well on practical examples. The authors trained this decision tree on MNIST. The pure self-decision tree mechanism achieved about 94.45% accuracy. With a distillation from the neural network, which was our teacher model, to the decision tree, which was our student model, achieved about 96.76% of the accuracy. This result is somewhere between pure decision tree's final score and pure neural network final score. One might wonder that the result itself is not that good enough, but this model shows other implications. These results can be interpreted as it has successfully shown that the knowledge of neural network can be successfully transferred to the decision tree model. The decision tree model has more interpretability. The filters at every node shows how the model is taking the decision on given inputs. One super clear example is the right one below. The filter shows the black color shape of 3, and black means the value is close to 0, while the white means 1. This will go left as input image with a number 3 will be multiplied to zeros, while 8, the left part of 8 will survive, which have larger value when filter is applied. Another interesting example would be Connect4 Dataset. You can simply think of this dataset as a board game like chess, and the input is a board state, and the output is the outcome of the game. So the task is to predict who might win at this board state. Let us talk about the interpretability of this model. First, filter has black parts at the centers and white things on the edges. These filters can be thought of as a model. Firstly, gets input and checks if the players had placed their pieces on the center or not. If they had allocated on the centers of the board, it will have lower probability of getting right, so it will go left. Otherwise, it will go right. So the model can be thought of as that they are checking the location of the pieces, and it is important in prediction of win or lose. That is what model thinks. So finally, this work has two main implications. First of all, interpretability. They have created a model with a larger interpretability. Hierarchical decision making is way more interpretable than that of a neural network. So at each node, we can interpret the way it works with binary decision making, which is do or not. And another thing is their performance loss is not that significant. This can be done by distilling the knowledge from the powerful neural network. In this way, we can still gain some of the benefits of deep neural networks by using them to improve the training of this explicable model. This is the end of our presentation, and thank you for your listening.